Okay, so just speaking about linear regression. In linear regression, you're trying to predict a variable y using the variable x. Usually, quite often, you assume that there's a linear relationship between y and x. Not exact. The data falls roughly about a straight line. So, confidence intervals for the slope. It's the estimate of the slope beta hat. That's the slope of the least squares line, plus or minus t sub alpha over 2, the estimate of the standard deviation of observations over the square root of sxx. T sub alpha over 2 is a critical value from the t distribution. The degrees of freedom is n minus 2. Testing the slope. Suppose we want to test the slope. If the slope is equal to some specified value, beta naught, against the alternative, there's a two-sided alternative. It's not equal to that slope. The test statistic is the estimate of the slope. Again, this is beta hat minus the hypothesized value over the standard deviation of estimated standard deviation of b. Again, this will have a t distribution with n minus 2 degrees of freedom if h naught is true. That's where you look up the critical value. Critical value could be either one-tailed or two-tailed. Confidence limits for the intercept. It's the estimate of the intercept plus or minus t sub alpha over 2. And this remaining part is the estimated standard deviation of alpha hat. Again, t sub alpha over 2 comes from the t distribution with n minus 2 degrees of freedom. Testing the intercept. Suppose we want to test if the intercept is equal to some specified value, alpha naught. The test statistic is the estimate of the intercept minus the hypothesized value over the standard deviation of A. A is the intercept of the least squares line. Confidence limits for other points on the regression line. This is the value on the regression line, the line that's going through the center of the data at x equals x naught. If x naught is 0, that's equivalent to estimating the intercept. There's the formula for confidence limits. It's a plus b x naught. That's the estimate of alpha plus beta x naught plus or minus t sub alpha over 2. And then the standard deviation of a plus bx naught is s square root 1 over n plus x naught minus x bar squared over sxx. Again, t sub alpha over 2 comes from the t distribution n minus 2 degrees of freedom. Prediction of y when x equals x naught. This is trying to capture the line that y is varying about, the y coordinate on the line the y is varying about. This is trying to capture the value of y. The difference is the 1 in front here. That makes it a bit wider so that it can capture the value of y that will be scattered about, alpha plus beta x naught. Correlation and regression are very closely related. If the correlation is high in absolute value, close to +1 or -1, the data falls almost perfectly along a straight line. There's the correlation coefficient. It's sxy over square root sxx syy. The correlation coefficient will range between -1 and +1. be actually equal to -1 or +1 if it falls perfectly along a straight line. So the properties of the correlation coefficient. The correlation coefficient will always be between -1 and +1. It'll be equal to +1 or -1 if the points lie on a straight line. If the line has positive slope, it'll be +1. If the line has negative slope, it'll be -1. The testing for independence, testing for zero correlation. There's the test statistic, square root n minus 2 r over 1 minus r squared, square root 1 minus r squared. If r is close to +1, this denominator here will be extremely small, and t should be large. We reject the hypothesis of independence if t in absolute value is large. This will be true if r is close to +1 or -1. This is a two-tailed critical region. You can also have a one-tailed if you were trying to prove that it had positive correlation or prove that it had negative correlation. Here's an example. Here we're looking at building fires, fires that occur in buildings in a city. And we're really interested in the relationship between how close the building is to the closest fire hall, X, and the damage. If the fire hall is quite a ways away, if X is large, then the amount of damage that would be done will be larger because it'll take more time for the trucks to get there. The data was collected for 15 fires. There, for each fire, we had the distance to the closest fire hall and the amount of damage done in thousands of dollars. You plot a graph of that, you can sort of see where. If you plot a graph of that, you can see that as distance increases, the amount of damage is going up, almost a straight line. So let's do some calculations. The sum of the x's distance is 49.2, sum of the x squared, 196.16, sum of the y's, 396.2, sum of the y squareds, 11376.75, sum of the xi's times yi, and then from there we can compute x bar, which is the average distance, and the average cost, y bar. We can compute these three sums. SXX is the sum of deviations of the x's from their mean. SYY, sum of deviations from the y's from their mean. Those are the computing formulas. SXY is the sum of product deviations. From that, we can compute the correlation coefficient. It's just SXY over square root. SXS, SYY, it's quite high. You can see that, I'll go back here, you can see that from the scatter plot. The scatter plot is lying very close to a straight line. The test for independence. The test statistic is square root n minus 2 r over square root 1 minus r squared. N was equal to 15, n minus 2 is 13, r was 0.961, t is 12.525. We're going to reject that if t is greater than t.025, 2.160, it is greater, so independence is rejected. The relationship between regression and correlation. There's the formula for the correlation coefficient. There's the formula for the slope, SXY over SXX. Multiply this by SYY over square root SXX. That's exactly the same thing. The square root SYY will cancel out with this, and square root SXX times SXX will be SXX. So this is really SYY over SXX times R. If I divide these by n minus 1, I'll get the standard deviation, and take the square root, I'll get the standard deviation of y over the standard deviation of x. So the slope is related to R this way. It's the ratio of the two standard deviations times R. The test for independence. There's the test statistic for testing for independence. Remember that beta hat is just square root SYY over SXX times R. R is square root SXX over SYY times beta hat. The two tests are exactly the same test. This is the test for zero slope. This is the test for independence. There's the test statistic for independence. Put in the formulas for R. Do some arithmetic calculation. You can then show that this statistic here is exactly the same statistic for testing for zero slope. So the two tests are exactly the same. Regression in general. Before we had one predictor variable, x, that was trying to predict y. Now let's consider having more than one predictor variable. This is something that occurs quite often in practice. We want a model that predicts that explains how y is related by x1 up to xp. You can use this for predicting, or you can use it for controlling. You know the relationship between y and x1, x2 up to xp. You can manipulate x1 and x2 up to xp that will determine the value of y. This is a general model. This is a function that's known except for these parameters, theta 1, theta 2 up to theta q. The epsilon terms are to model the fact that it won't be perfectly related. Y won't be perfectly related from F1, F2 up to Fp. So there's usually some error. That'll be epsilon. It'll assume to have a normal distribution, mean zero, standard deviation sigma. Example. Suppose we have blood pressure in H. This is we'll assume a simple linear regression model. So this is the function of x, alpha plus beta x. It's a linear function. That's a simple linear regression model. That'll be appropriate if the data is falling roughly about a straight line. The line is alpha plus beta x. We don't see that. We just see the data. We want to estimate alpha plus beta x. Another example. Suppose y is the best 5 times for running the 100 meters. X is the year. There's a graph of x and y. over the years. This is an exponential regression model. The curve here is an exponential curve. An exponential curve flattens out at a limiting value, and it rate of decrease goes down as time goes on. So this is the function of x that we're trying to fit. Gamma is really the limiting value of x. Alpha is the height above that limiting value at time 0. Another example. We're looking at mileage on a car brand and how it depends on engine size, horsepower, and weight. So we'll assume that the relationship is a linear relationship between y and the 3 variables being measured. If you increase the engine size, mileage will go down. If you increase the horsepower, mileage will go down. If you increase the weight of the vehicle, mileage will go down. Whereas if the rate of decrease is constant, then it'll fit a linear model. Nonlinear models occur when the rate of increase is varying. So there's the multiple linear regression model. The multiple linear regression model assumes that y is a linear function of the variables x1, x2 up to xp. The constants beta naught, beta 1, beta 2 up to beta p are unknown and have to be estimated. The random error term is assumed to be mean 0 standard deviation sigma. The importance of the linear model. One is the simplest form of a model, which each dependent variable has some effect on the independent variable y. So when fitting models, usually one starts with a linear model. Another importance, quite often could be the most appropriate model. This will be true if the dependent variable y increases at a constant rate as any of the independent variables is increased, while holding the other independent variables constant. If that's the case, then it will form a linear model. Many nonlinear models can be linearized. They can be put into the form of a linear model by taking transformations of either the dependent variable or the independent variable. So quite often, many nonlinear models can be changed into a linear model by taking transformations. Common transformation is the log transformation. It quite often straightens out data. Here's an example. Here we're measuring the concentration of phosphorus in corn plants. So the dependent variable is the amount of phosphorus that's in each of the corn plants. The predictor variables are the amount of phosphorus that's in the soil. And it could be in two forms, inorganic phosphorus and organic phosphorus. So these were measured on 18 test plots. The amount of inorganic phosphorus, X1, the amount of organic phosphorus, and the amount of phosphorus that resulted in the plants that were growing there. There's the data for the 18 test plots. There is a linear model fit to that. the coefficients. This is the constant term. It's really the amount of phosphorus that you'd expect in the plant if the inorganic phosphorus X1 and the organic phosphorus X2 was 0. The coefficient of X1 is how much Y increases per unit increase in X1. The coefficient of X2 is the amount that Y increases per unit increase in X2. There's actually a plot of the data, three-dimensional plot. There is the fitted linear model. I'm basically fitting a plane through that scatter plot. The multiple linear regression model. It assumes that Y is linear related to X1, X2 up to XP. The parameters beta 1, beta 2 up to beta P, and beta naught are unknown parameters. The random term epsilon is just modeling the departures from that perfect model, possibly due to other factors. It's assumed to have a normal distribution with mean 0 and standard deviation sigma. If sigma is larger, the random departures are larger. These are the statistics that you get from multiple regression. The least squares estimates. These are the values, once you've got the data on X1, X2 up to XP, and the data on Y, Y1, Y2 up to YN. The residual sum of squares is when you pick values for beta naught, beta 1 up to beta P, and use those values to predict the value of Y from the values of X1, X2 up to XP. And if you choose the coefficients beta naught, beta 1 up to beta P to minimize this residual sum of squares, these are called the least squares estimates of the parameters. It's similar to when there's just one variable. You just have an intercept and one slope. Here you have P slopes, a slope for each of the independent variables. Another set of statistics, the analysis of variance tables. This tells you the sum of squares. This is measuring the variability in the Y values. The residual sum of squares, it's measuring the variability in the Y variables that's unexplained by the X variables. Another, the regression sum of squares. Here it's similar to the total sum of squares, except we put in the predicted values of Yi in place of Yi. Now you can show that the total sum of squares is the regression sum of squares plus the sum of squares for error. The regression sum of squares is usually called the variability in Y that's explained by the X values. If the X values predict exactly the Y values, the total sum of squares and the regression sum of squares will be the same. And the residual sum of squares, the sum of squares for error, will be 0. So these are some statistics that will come out of fitting data. There's the ANOVA table. Mean squares are just sums of squares divided by degrees of freedom. The sum of squares, the mean square for error, is an estimate of the parameter sigma. This statistic here is used to test whether the predictor variables have any effect on the dependent variable. So the uses of this table: to estimate sigma squared. It'll be just the mean square for error. To attest the hypothesis that the regression coefficients are all zero, meaning that all of the independent variables have no effect on the dependent variable. To use that, use the F statistic MS regression over the MS for error. We reject the null hypothesis that all variables have no effect. If F is large, greater than F sub alpha, the degrees of freedom in the numerator is P, the degrees of freedom in the denominator is N minus P minus 1. Those are just the degrees of freedom in the analysis of variance table. You can also use this to compute some important statistics. The sum of squares for regression over the sum of squares total. That's the sum of squares regression over sum of squares total. That's the coefficient of determination. It's the proportion of variance in y that's explained by x1, x2 up to xp. If the predicted value of yi was exactly the same as the exact value of yi, this would be equal to 1. 1 minus r squared is the proportion of variance in y that's left unexplained. Sum of squares for error over sum of squares total. Sometimes people like to use another statistic called r squared adjusted. It's adjusted for the degrees of freedom. It's 1 minus ms error over ms total. It's measuring the proportion of variance in y that's explained by x. Another statistic is the square root of r squared. That's called the multiple correlation coefficient. It's the maximum correlation between y, the dependent variable, and some linear combination of x1, x2 up to xp. These statistics are all equivalent. You can calculate, if you know one of them, you can calculate the other one. Using statistical packages. You have to use a package because the equations for finding the least squares estimates are big. So to use Spss, you can also use other packages, Minitab. After starting up Spss, you open up the data. If the data is in an Excel file, pick Excel. Up will come this dialog box. If the variable names are in the first row, you click that. And if the data is in a certain range, you specify the range. If you leave that blank, it'll just read everything in the table. Here, I've opened up a file. This is a file on automobiles. One of the variables is miles per gallon. Other variable is engine size, horsepower, and weight. There's the data that came from that file. And what we're interested in doing is predicting miles per gallon from engine size, horsepower, and weight. To do this, to perform analysis, you go analyze, and you pick regression and linear regression. There's other forms of regression. This is where you're fitting nonlinear models and so on. So I'll pick regression and linear regression. Up will come this dialog box. Here you have to tell the program which is the dependent variable. The dependent variable is miles per gallon, and the predictor variables, the independent variables, are engine size, horsepower, and weight. So you put miles per gallon as the dependent variable, engine size, horsepower, and weight as the predictor variables. One other thing is You have to choose a method. If you select enter, it'll use all three variables to predict miles per gallon. You can also use some more complicated methods: forward selection, backward elimination, stepwise regression. These are methods to try and find the best equation. In forward selection, you start with nothing in, and then it'll add variables one at a time that are important until none of the remaining variables are important. Backward elimination will do it the other way. It'll start with everything in, and then delete variables that are unimportant. And then stepwise regression is a combination of both. It'll start with nothing in, add variables, but after it's added a variable, it'll use backward elimination to see if any of the variables added at earlier steps can be removed. So if you click on enter on the method, you can select these methods. The method enter will enter everything. Stepwise, backward elimination, forward elimination. Stepwise are other methods. So forward selection, this starts with no variables in the equation, carries out tests on variables that are not in the equation to see which have a significant effect, and then it adds the most significant one. Continues until all variables not in the equation have no significant effect on the dependent variable. Backward elimination, this starts with all variables in, then carries out tests to see which variables have no significant effect, deletes the least significant, and continues until variables in the equation all have a significant effect. Stepwise is a combination of both, uses both forward and backward. Starts with no variables in, carries out tests, adds the most significant, then after it adds a variable, it checks to see if any variables added earlier can be deleted. This is the usual one that people like to use. All of these methods are trying to find the best equation. The best equation is the one that's simplest, doesn't contain variables that are not important, but it's adequate. It contains variables that are important. So once the dependent variable, the independent variables are selected, and the method is selected, you press OK, and the analysis will be performed. Here's one of the tables that comes out. R squared adjusted. The standard error of the estimate, this is the estimate of sigma. R squared and R squared adjusted are measuring the proportion of variability in the dependent variable, miles per gallon, that's explained by three predictor variables: weight, horsepower, and engine. So that's about 67%. R is the multiple correlation coefficient. It's the maximum correlation between y and some linear combination of x1, x2, up to x3. The next table is the analysis of variance table. From that, R squared adjusted can be calculated from those entries. R squared is just the regression sum of squares over the total sum of squares. This is the F statistic. It's the ratio of the mean square for regression over the mean square for total. It's testing whether all the predictor variables have no effect on the dependent variable. Here's a final table. This is giving you the estimates of the regression coefficients and their standard error, and test to see if the regression coefficients are 0 or not. looks like engine size is not significant. Its p-value is not less than 0.05 or 0.01. All that means is that once you've got horsepower and weight, engine size is not important. So from that, you have the equation for predicting mileage from engine size, horsepower, and weight. The fact that these coefficients are all negative means that if you increase engine size, horsepower, or weight, you decrease mileage. For every 1,000 units in engine size increase, mileage will be decreased by an average of 5.53 units. For every 100 increase of 100 units in horsepower, mileage will be decreased by 5.56. For every increase in weight of the vehicle by 1,000 units, mileage will be decreased by 4.62. The constant term is really the predicted mileage for a car that has 0 engine size, 0 horsepower, 0 weight. So there's the equation for predicting mileage from engine size, horsepower, and weight. The coefficient of engine size is not significant. P is equal to 0.432. The other two are. I'll give some examples next time. The final assignment involves fitting a linear model. The final assignment, the first question, has as the dependent variable. Well, I'd have to check on it. Okay.
I have a question.
Sure.
Is there going to be like a lab that's going to explain more about the assignment?
Yes.
Okay.
Okay.
And also I just got one more. When are the marks back for test 4?
They should be back this afternoon sometime.
Okay. I just thought for a second that I must have not submitted my answers, which I did, but I just feared that.
Okay. Yeah.
Is that the case?
That's obviously a common fear, but
yeah.
Okay. Okay. The marks will be posted sometime, probably this afternoon. The next topic is logistic regression. The simple linear regression model. That's predicting a continuous dependent variable from an independent variable X. The multiple linear regression model is extending the number of predictors from one variable X to P variables, X1, X2, up to XP. Sometimes the dependent variable is not a continuous measurement. Sometimes it's just a binary measurement, successor failure. Basically, this is where logistic regression comes in. The dependent variable is no longer a continuous variable, but it's categorical. In particular, it just has 2 categories. Where I've seen this used is in sports. We're looking at people playing sports, hockey, football. The dependent variable is whether they suffer a fracture, bone fracture. So success, they do suffer a fracture. Failure, they don't suffer. Success and failure are just labels. And you may want to predict whether a person will suffer bone fracture from other variables. The age of the individual, maybe as the age goes up, there's a higher chance that they'll suffer a bone fracture. It might also depend on the person's weight and height. So that would be another example. In cancer, the variables that you might want to use to predict might be certain blood measurements, counting the frequency of certain types of cells in the blood. And what you want to do is predict whether the person goes into remission or doesn't go into remission. So these are all ones where the dependent variable is not continuous, but just has two outcomes, success or failure. So this is where logistic regression comes into play. And you can extend logistic regression to more than one predictor variables to where you have several predictor variables. I'll be giving some examples later on. So maybe at this point, we'll sort of end the lecture. And I'll answer any questions.